So I'll be taking you through my MATLAB project. This MATLAB project is a simulation of a simple harmonic oscillator. And a simple harmonic oscillator is just a mass attached to a spring, as shown here, and they generally exhibit this kind of motion, as can be seen here on a graph. And so this simulator does pretty much exactly that. It's an animation of this graph, and what takes it one step further is that, as we see here, this is a position equation for the simple harmonic oscillator, and the derivative of that gives velocity, and the derivative of velocity gives acceleration. And so in the end, the goal of this project is to create this program that the user can input a desired amplitude, a desired frequency, and a desired time, and a desired phi in radians to generate graphs of the position, velocity, and acceleration. This is useful because you can not only test to see how simple harmonic oscillators work and how the different variables affect the oscillation, but it's also a good tool just to see the relation between position, the derivative, velocity, and derivative again, acceleration, so the first and second derivatives and third derivatives and so forth. So without further ado, we'll start this up. It's called just by SHS for the simple harmonic simulation. And so here at the start it asks that saying that all the variables need to be clear, just giving the user a warning. This really, I must say, isn't entirely necessary, because the reason why this has to be cleared is if this program is running multiple times, the movie, in the end, this is going to be used using a movie function, which I'll explain later, and it holds all the frames for a certain time. And so if you say you want a graph that goes over a certain amount of time that's longer, and then the second time you want something that's shorter than the first one, then the movie will play both the short time and then the longer time after that. So in the end, it's just the movie that needs to be cleared, but just for some added complexity, I added this here. So I guess we can start with saying that we don't want to continue, because maybe we have some variables that we need to get saved, so we'll just type in n. So then the program tells us that nothing's been done to save our variables, and run this again by typing SHS again. So I guess we'll do what it says and type in SHS, and so this time we'll say alright, we'll continue this time. So here it says, okay, enter desired amplitude. We'll say we want a 5-meter amplitude. Then the mass of the object here will take 2 kilograms. The K constant of the spring, I don't think I said that earlier, but it's also another factor in this graph generation. So we'll say we want it to be 2. And for phi, we can say 1.6. And we'll want it to go for 10 seconds. And what's kind of interesting here is it gives us an estimated angular frequency, which kind of interesting, comes out to just 1. So that's pretty cool. But then it asks how many times it wants us to live the movie, because in the end it's not really just the graphs that are being generated, but it's actually going to be an animation, as you can see how the different time points line up with each other in terms of the position, velocity, and acceleration. So just to make it clear, we'll loop it 4 times. So when this happens, this is a graph. So we can see here that this is the position in meters, and as you can see here, this goes like that. And this is going to loop 4 times again, so as we had said. So we can see how each point is going at the same time interval and meeting at the same time. So we can see the relations here. So velocity is max here, so this position is going fast, and acceleration is max here. This is changing direction. So it's just kind of interesting to see all of how these graphs are related to each other. So I think this thing is going to keep looping. I can probably go right now and show how this was coded. If I can go, here we go. So here's the code for it. It's kind of messy right now. I'll probably organize it more later. But pretty much this block right here is just all the text. It's saying this is the simulation thing. Here it's asking for a response the yes or no. I have it here as with an if statement saying that if it's empty or you put a capital Y or a little y, the response is going to be this yes, and it's going to follow through doing all these things. And so here it's asking for an input for amplitude, there's mass, there's the K, there's the P, there's the T, there's angular frequency, and the R. Here it's also saying that here's angular frequency, and it's going to show that this is where it showed that this is the angular frequency over here, just for reference, so you can maybe reconstruct the equation later if you feel like. Interestingly enough, the square root, I guess, of this worked because obviously 2 over 2 is 1, so that's how it came out to be. So R is just how many repetitions we want. So we'll move on forward. So this is really like the core of this animation right here. We have K here just as a kind of a dummy variable to keep looping here, and it goes to T, and this T was the T that was set by the user earlier on. So we have that subplot here. Just subplot here to start making those 3 graphs, and we plot. This is the first position one here. These are just the marker colors and the edge, and we say hold on, so we can also add in the second plot. So this plot right here, so in the end we're actually making 2 plots in this graph. One plot is the actual line of the position, velocity, and acceleration, and here actually, as we can see, is this is actually going to plot just 1 point at a time. So what this does is so we have all the labels here as well, but in the end where this is going to go, I'm going to skip ahead a little bit, is it's going to move into this using this movie function, or this M function or variable we have right now, which is using get frame, and pretty much all this is it just takes a picture of this frame. So technically what's going on is that this is going in, it plots just 1 point, and makes all the marker edge colors, adds in the other one, and then it'll do the same thing for the velocity and acceleration. This is just why this is here. And so same thing, 1 point for position, 1 point for velocity, 1 point for acceleration, and it'll capture that frame here. And then as this is told to loop, it keeps going, and the time constants are going to keep moving up, and the time variable is just going to move up by 0.1 is seeing here. And so in the end, what's happening is that the same equation is being graphed every time, but the points keep moving forward each time in the loop, and then a frame is being captured for it. And so in the end, what happens is CLF here in the axis position is just to position the movie, or position the movie correctly, because what I was having a big issue was that it would only play the frames captured. Well, play all the frames captured, but it would center around the last active plot, so it would be centered around here, and you couldn't really see anything over here, so that kind of sucked. So this changed the position, so it'll be centered perfectly like we'd like it. So in the end, all that remains to be done is just say movie. This is just the function, just movie of M, and M are just all the captured frames, just the collection of all the captured frames we did, and R is the amount of repetitions which was inputted by the user up here. And so in the end result is that looks like those, as we see, the red, green, and yellow dots moving around, kind of simulating the oscillation going back and forth due to the repetitions that were set before by the user. And so here at the end is that else statement, where if they had said no all the way up here, then just these statements were displayed. And that's really it. That's the core to the program. I'm going to run it again real quick just to show just how all the graphs are kind of made. We'll just loop this 4 times, I guess. And so as you can see here, well, this is kind of weird. I don't know why this is doing this, but as you can see here, everything's labeled here correctly. This is acceleration, meters per second squared, or meters. Uh oh, this is mislabeled. This should be meters per second squared, but I'll change that. and 10 seconds, and there it is, how they all lap. And you see, notice how this graph went by faster, and that's because the time was set to 2 seconds, and so this thing finished pretty quickly. And I think that's all that remains to be said about this project. Hope you enjoyed it, and thanks for listening.